Let us discuss one of the important inequality. It is known as Chebyshev inequality. It has wide applications. Later we will see that some of the applications. So it says that if x is a random variable with mean mu and variance sigma square, then for any positive number epsilon, we have probability that x minus mu greater than equal to epsilon is less than equal to sigma square by epsilon square. So it is any random variable. Let x be a random variable with mean mu and variance sigma square. Then for any epsilon greater than 0, probability that absolute value x minus mu greater than equal to epsilon is less than equal to sigma square by epsilon square. So that means it is giving some probability that how random variable may be taking values away from the interval mu minus epsilon, mu plus epsilon. This probability should be less than equal to this sigma square by epsilon square. So what is the proof? Let us prove this. It is not very difficult. Let us consider this continuous random variable, then we will do the integration. For discrete case it will be sum, but it is very similar proof. So let us consider, let x be a continuous random variable with the probability density function f of xx. Then what is sigma square? The variance of x is given by so this is sigma square. By definition this is nothing but x minus mu whole square. Mu is the mean, x minus expected values of x minus mu whole square. So what is the definition? Because it is a continuous random variable, otherwise for discrete case we will take sum, but it is continuous random variable, it will be minus infinity to plus infinity x minus mu whole square fxx dx. So this is the variance formula. Now see that this is the sum of a positive number, fxx is also positive, this is also positive. So if you it is like a integration over the region, all are positive number. So if you do the integration in a particular subset of the real number, then this value will be, because we are always adding, so that's why this will be always greater than equal to if you take a subset of the random value. So this set we are considering all these x such that x minus mu is greater than equal to epsilon. So in this region if you do this integration, because the remaining part also it may be contribute some positive number, there is no cancellation. So that's why it will be always greater than equal to, in this interval if you do the integration, fxx dx. Now in this interval, so basically we can do the x such that x is a real number such that x minus mu, so we can write. So in a other way you can also, so okay, so x belongs to real number such that x minus mu is greater than epsilon. So now in this region where we are doing integration, x minus mu is greater than equal to epsilon in this region. So greater than equal to epsilon. So if you take the square both side, whole square, this will be greater than equal to epsilon square. Hence in this region if you do the integration, x minus mu greater than equal to epsilon. So let us write this simplified for x minus mu greater than equal to epsilon. So this is x minus mu whole square is greater than equal to epsilon square. So this will be epsilon square fxx dx. So epsilon square, because this value is greater than equal to epsilon square, so this integration will be also greater than equal to epsilon square. So now integration will be greater than equal to this integration. So now this is equal to epsilon square into epsilon square, this will equal to epsilon square into x minus mu greater than equal to epsilon fxx dx. Now what is this? So if you do, it is a density function, this is some set, If you do the integration, we know that with by the properties of the density function, this is nothing but epsilon square into this random variable taking value greater than equal to epsilon. So then from whole part we get that probability that x minus mu greater than equal to epsilon is less than equal to, so from here it is greater than equal to epsilon sigma square by epsilon square. So this is called the Chebyshev inequality. It is the proof. I think it is very straightforward, you can go through again. So very simple, some of the steps. So now we will see that how it can be utilized. So this inequality is important. So some numerical example, let us see some numerical example here. So a pair die is thrown 600 times. Let x be the number of sixes obtained. So whenever you are throwing a pair die 600 times and x is number of 6. So pair die means every time you are throwing a die and 6, what is the probability that every time 6 can be obtained? So number of times that 6 can be, then probability that x can be taking this value 6. So this is nothing but 1 because it is a pair die. So all side equally likely. So 6 can be 1 by 6. So hence, so suppose this is, let us consider some other random variable y is equal to once you are throwing, and x is the random variable number of 6. So x is the, so basically it can be ith time you are throwing the die, then 6 occur 1 by 6, but x is the 600 time you have thrown the die. So this is yi, I is equal to 1 to 600. So we know that it is nothing but binomial distribution with parameter 600 and this is 1 by 6 is the probability every time. So now it is asked that find the lower bound of this value, x be the number. So x is a binomial distribution with because 600 time n 600 time and p 1 by 6. Now we have to find lower bound of this probability. So find the lower bound of x is greater than, so it is asked that find a lower bound of, so let us write down that find a lower bound of, probability x less than 120 and greater than 80, greater than 80. So now x can be, sorry, x can be, x is less than 120 and greater than 80. So now this probability always lower bound, we know that probability is always greater than equal to 0, but we do not want this lower bound, it is a non-trivial lower bound, we want some non-trivial lower bound. Now how we can do this, how we can find this lower bound? Now let us find what is the expected values of x. So mu is equal to, let us denote expected values of x, this is, we know that it is np for binomial case, whenever x is binomial np, in that case n is equal to 600 and p is equal to 1 by 6. So this is 600 into 1 by 6, this is equal to 100. Then what is the variance? Sigma square. Sigma square, we know that variance of x, this is npq. So this is 600 into 1 by 6 into q is nothing but 1 minus p, this is 5 by 6. So q is 1 minus p, so 1 minus 1 by 6, this is 5 by 6. So then we can simplify these things. So 6 is 100 and then okay, so this will be nothing but, so just okay, let us keep it is 500 by 6, later we will simplify it if required. So sigma square is this. Now Chebyshev inequality says that x minus mu. So now what is x minus mu? So here we want probability that x less than 120 greater than 80. So then this is equal to probability that, suppose mu is here 100, if you subtract 100 x minus mu, then this is become 120 minus 100 and then this is 180 minus 100. So this is equal to probability that minus 20 less than x minus 100 less than 20. So basically the probability is absolute value x minus 100 is less than 20. Now these things is nothing but 1 minus of probability that the complement of these things x minus 100 greater than equal to 20. So for this case we have some by Chebyshev inequality. We know that by Chebyshev inequality we have for any epsilon greater than 0, probability of x minus mu greater than equal to epsilon is less than equal to sigma square by epsilon square. Now if you both side, if you do 1 minus, then we will get 1 minus probability of x minus mu greater than equal to epsilon will be it will be opposite, greater than equal to 1 minus of sigma square by epsilon square. First of all we can do minus of this less than, it will be greater than equal to, then we can add 1. So this is the, so this is nothing but which implies this is the another version of this, but it is same actually, just this complement x minus mu less than epsilon, it is greater than equal to 1 minus sigma square by epsilon square, because it is the complement of these things. Now here you can see that we want to find mu is here 100, mu is here 100, and we want what is this. So let us keep at it, because we have we can use these things also in Chebyshev inequality. From Chebyshev inequality, what is the next this is the another way of writing this. So that also we have found here the lower bound, it is the upper bound for this case, this complement part also we did that. Hence here x minus 100 and less than 20 we want. So then epsilon is nothing but 20, and sigma square also we know, sigma square is here, sigma square is 500 by 6, 500 by 6. So hence we know we get that probability that x minus 100, this absolute value, less than epsilon is 20, this is greater than equal to 1 minus sigma square is 500 by 6 into epsilon square is 20 square. So then we just cancel this. So then we get, so this is nothing but 1 minus 5 by 24. So 24. So this is 24 minus 5. So 19 by 24. Hence what we got finally. So we wanted to get this probability, lower bound of this probability. This is the question. Thus find the lower bound of this probability. This probability same as this probability, same as this probability, and same as this probability. And finally what we found, this is get by Chebyshev inequality, what we found that this is greater than equal to 19 by 24. So this is the some of the application of the Chebyshev inequality. So some more application we will discuss in the later whatever what we learn. So most of the part of this course actually we mostly completed. So next remaining things we will discuss, it is the notion of convergence. So some of the random variables, and what are the some of the law. So law of large numbers, like for law of large numbers, and also strong weak law of large numbers, strong law of large numbers. Also we will discuss the central limits theorem, and we will complete this course. So with some more numerical examples.